This is the second lecture in section 1.2, and in this lecture we are going to look at the structure, bonding and properties of the first 20 elements in the periodic table. The first learning outcome is that you should know where to find the metals, non-metals, halogens, noble gases and transition metals on the periodic table. And of course you use your data booklet to help you. But unlike National 5, you don't actually have a periodic table in your data booklet which splits the periodic table into the metals and non-metals. So it's important that you're able to do that yourself. So everything above this line are non-metals. So hydrogen's a non-metal. And then when we get over here, aluminium's a metal, boron's a non-metal. So we then zigzag down the periodic table. Okay. So everything up here, and hydrogen is a non-metal. Everything down here, including these, are metals. The halogens are the elements in group 7. Noble gases, the elements in group 0. And the transition metals, well, in this table they're labelled as transition elements. They are all metals, so transition elements, transition metals, same thing. So that's all these, all the elements in between group 2 and group 3, including these ones down here. Okay, they're all transition metals as well. The next learning outcome was that you should be able to explain the reactivity of elements by considering their electron arrangements. You've got a table in your data booklet which gives you all the electron arrangements, and really all this learning outcome is saying is that most of the elements in the periodic table do not have a full outer shell of electrons, and so they will undergo chemical reactions in order to gain a full outer shell. Metals will lose the outer electrons to get a full outer shell. Non-metals will gain electrons to get a full outer shell. Hydrogen's a bit of an anomaly there. It's a non-metal, but it does tend to lose electrons to become an H+ ion. And the only elements which don't undergo chemical reactions, don't form chemical bonds, are the noble gases in group 0, because they all already have a full outer shell of electrons. Right, so the bulk of this section was about knowing the bonding structure and properties of the first 20 elements. So we're going to split it up into 4 different groups. First, we're going to look at the metallic elements. So here's a wee clipping of the periodic table showing the first 20 elements plus bromine and krypton. So we'll circle in red the metallic elements, and they are lithium, sodium, potassium, beryllium, magnesium, calcium and aluminium. So all 7 of these elements have basically the same bonding and structure. Right. The bonding is known as metallic bonding. And the structure, you normally talk about a metallic lattice. A metallic lattice is made up of positively charged metal ions and delocalized electrons. So like for example, if this was sodium, it would have lost its outer electron, become 2,8, giving you a Na+ ion, and this is the delocalized electrons are the outer electrons that the metals have lost. Metallic bonding is very strong, so in order to melt or boil a metal, you have to break the metallic bond, and because it's strong, metals tend to have high melting boiling points. So we have high melting points and boiling points. The other important property of metal elements is the fact that they conduct electricity even when solid. So they conduct electricity when solid. Nothing else will, apart from graphite, which we'll talk about later on. And they can conduct electricity when solid because they have these delocalized electrons. Delocalized means they're not fixed in one position, they can move around. Okay. So they can move around and carry electric charge through the metal. So that's the main properties of those 7 metal elements. Okay, now we're going to look at another set within the first 20 elements, the monatomic elements, and we'll give them a sort of orangey circle. And they are the noble gases: helium, neon, argon, and we'll include krypton. Okay. And they all have the same bonding structure and properties. The bonding is known as monatomic. And they don't actually have a structure. Because monatomic means, well, they don't actually bond. They just go around as single atoms, one atom, hence monatomic. So if we had a big beaker here full of, say, neon, so there's one neon atom, there's another neon atom, there's another one, there's another one. They're not bonded together. Okay, they're quite happy on their own. So what properties does this give rise to? Well, it means because there's no strong force holding the atoms together, they're very easy split apart and turn into gases. So they're all noble gases, they're all gases at room temperature. So they all have very low melting boiling points. However, if you do go to a low enough temperature, they will solidify. So you can get them to freeze. You've got to go to very low temperatures to get them to freeze. But if you do, they will all pack together closely. Which tells us there must be some attraction between the atoms. Okay. Now, this attraction, we don't refer to it as an intermolecular force when it's a noble gas, because noble gases aren't molecules. So the more general term to cover intermolecular forces, which includes the forces between atoms in a noble gas, are van der Waals forces. And the particular van der Waals force that exists between the atoms of noble gases are London dispersion forces. So let's remind you how London dispersion forces arise. Well, the electrons orbiting the nucleus of an atom are always on the move. Here we've got 2 electrons, so presumably it's a helium nucleus. If we could freeze it instantaneously in time, at some stages both electrons might be over the same side of the atom, making this side of the atom slightly negatively charged, and this side with no electrons slightly positively charged. So we give it the symbol delta minus on the left hand side of the atom and delta plus on the right hand side of the atom. And that can then, it says here it calls it an instantaneous dipole. We actually refer to it as a temporary dipole. But that temporary dipole can then induce a dipole in another helium atom, because the electrons going around this atom will be attracted to this positive charge. So they'll be over this side of the atom, giving it a slightly negative charge, leaving this side slightly positive charge. So you get this temporary dipole and it induces a dipole in another atom. So you then get an electrostatic attraction between the slightly positive end of that atom and the slightly negative end of that atom, because opposites attract, so positive and negative will always attract each other. And that attraction there is the London Dispersion Force, or LDF for short. It's not very strong, but it is strong enough to pull these atoms together if you go to a low enough temperature. We refer to it as a temporary dipole because of course these electrons are not frozen there. They will continue to move. So this dipole will disappear, then reappear again, then disappear, then reappear. So it's not always there, it's just a temporary dipole. Also, if we look at the melting boiling point of noble gases, we see that the London dispersion force increases with the size, the mass of the atom. As the atom gets bigger, it's got more electrons in it, so the size of the London dispersion force can get bigger. So like krypton has got a higher melting boiling point than say helium because it's a bigger atom, so it creates a stronger London dispersion force. Okay, so we've got all the metals, we've got all the monatomic gases. The next set we're going to look at are the covalent molecules, and we'll give them a blue circle. So lots of covalent molecules in the first 20 elements: hydrogen, nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine, and we'll include bromine. So they all have much the same structure and bonding and properties. So the bonding is covalent because they're non-metals. The structure is molecular because they form molecules as opposed to covalent networks. But they don't all have the exact same type of molecule. So if we look at these four, hydrogen, fluorine, chlorine and bromine, they all have a valency of 1, they all form one bond, so they all form a nice simple diatomic molecule with one covalent bond between them. So right, there's H2, F2, Cl2, Br2. Oxygen and nitrogen, however, have got a valency of 2 and 3 respectively, so they form slightly different diatomic molecules. Oxygen's O2, but it's got a double bond between the atoms, and nitrogen, it's got a triple bond between the atoms. And the final two were phosphorus and sulfur. Well, phosphorus, like nitrogen, has got a valency of 3 because it's in group 5, but it forms a P4 molecule with this sort of tetrahedral structure. So phosphorus is P4. Okay. So it's not diatomic. All these other ones are diatomic. Phosphorus has got 4 atoms in the molecule. And sulfur, although it, like oxygen, it's got a valency of 2, it doesn't form a little S2 molecule with a double bond. It forms this ring of an S8. Each sulfur has got 2 bonds, as it has to be because it's in group 6, like oxygen, so it forms 2 bonds. But so it tends to form this cyclic S8 molecule. Okay. Now they're all covalent substances, they don't conduct electricity, they tend to have quite low melting and boiling points. But again, the strength of the intermolecular force will determine how low the melting boiling point is. All the molecules here are non-polar because it's the same atom bonded to the same atom, so these have the same electronegativities. So it's a perfectly non-polar bond, pure covalent bonds. So we haven't got any of those PD-PD or hydrogen bonds, which we'll talk about later on. The only intermolecular force going is the London dispersion force, which is always present between any molecules. And of course, it depends on the mass of the molecule. The bigger the molecule, the bigger the London dispersion force. So hydrogen, fluorine, chlorine, they're all gases at room temperature, but bromine is a liquid at room temperature, because the bromine atoms are a lot heavier than the chlorine, fluorine, hydrogen, so the London dispersion forces are strong enough to make it a liquid at room temperature. Oxygen and nitrogen are gases, but phosphorus and sulfur are both solid at room temperature, and that's because they form relatively large molecules. So though phosphorus itself is not that heavy, the molecule contains 4 phosphorus atoms, and so it is heavy enough to have a strong enough London dispersion force to make it a solid at room temperature. And sulfur, forming an S8 molecule, is plenty big enough to have strong enough London dispersion forces to make it a solid at room temperature. Okay, so the final group we have to look at are the covalent network elements, and we'll give them a sort of purple circle. So just 3 of them: boron, carbon and silicon. So the bonding is covalent, but the structure is not molecular, it's a network. And what this picture is trying to show is there's billions and billions of atoms joined together with strong covalent bonds. It could be all carbons or all borons or all silicons, but billions of atoms all joined together by strong covalent bonds. So if you want to melt or boil this, you have to break a strong covalent bond. Okay? Not a pathetic intermolecular force, but a strong covalent bond. So they're really hard to melt and boil. They have very high melting and boiling points because you've got to break a strong covalent bond, not a weak intermolecular force. Okay. Just going to look at carbon in slightly more detail, because as you remember, carbon forms several different networks. So carbon in fact can come in the form of diamond, graphite or fluorine. As diamond, each carbon is bonded to 4 other carbons, as you expect, is in group 4, valency of 4. This diamond forms this very strong structure, one of the hardest materials, in fact probably the hardest naturally occurring material. But not all carbon comes in the form of diamond. It can also come in the form of graphite. And in graphite, each carbon is only bonded to 3 other carbons, okay, within this layer. So there's a 4th electron for carbon, which 4th outer electron of carbon, which isn't involved in covalent bonding. And that 4th electron exists in between the layers, and it's delocalized, which is why graphite can actually conduct electricity when solid. So graphite has these very strong covalent bonds within the layers, but relatively weak attraction between the layers, which allows it to be used as a pencil, because as you write with a pencil, you shear a layer of graphite off the lead and onto the paper. The last form of carbon is fluorine, which is very different. This is a C60 spherical molecule. The important word there being it's a molecule, it's not a covalent network. Diamond and graphite are covalent networks. This is a covalent molecule. So a far lower melting boiling points than the networks. It'll still be solid at room temperature because it's C60, so that makes it quite a big molecule, but it is a molecule. You get slightly other designs of fluorines, maybe with C70 or C80, but C60 is the most common one. So here's a summary of the bonding and structure of the first 20 elements. plus these two. You need to know this, okay? But also please remember a little blue splodge for the carbon, because it sometimes is a molecule if it's in the form of fluorine. So carbon's not entirely a covalent network, it can also be a covalent molecule when it's in the form of fluorine. Okay? So remember things like phosphorus is a P4 molecule, sulfur is an S8 molecule. Okay. And the final learning outcome was I can use my knowledge of bonding structure to discuss physical properties of elements, melting points, boiling points, etc. For example, why sulfur has a higher boiling point than chlorine in terms of LDF? Well, I think I've already covered that. Sulfur is S8, so it's a big molecule, strong London dispersion forces compared with chlorine, which is just Cl2. Okay? And of course, when you're boiling a molecule, you're not breaking the strong covalent bonds within the molecule, you're breaking the relatively weaker intermolecular forces between the molecules. And in the case of elements, the intermolecular force is going to be London dispersion force, and it will depend on the size of the molecule in terms of mass.